In the last video, we said that one of the big calculus questions that we want to answer is, how do we find the slope of a tangent line? That right now we don't know how to do. So we're going to fall back to something that we do know how to do. We do know how to find the slope of the secant line, which that formula is given right here again. That's just the slope formula. And we know a little bit about limits by this point. So in this video, my goal here is to use what we know, which is the slope of the secant line, and we know about limits, and see if I can use those two things to help me find the slope of the tangent line. So here my function, we're going to work with a relatively nice function here, f of x equals x squared. Part A asks to find the slope of the secant line between x equals 1 and x equals 2. And this is something that we already know how to do. We said here is the slope of the secant line formula. So I can just go ahead and plug in x equals 1 and x equals 2. So f of 2 minus f of 1 divided by 2 minus 1. Here, f of 2 and f of 1, I'm going to have to plug those into my function f of x here, so I'm just going to square those two numbers. I'll have 2 squared minus 1 squared all over 2 minus 1. Well, that's just 1. 2 squared, I've got 4 minus 1 over 1. 3 over 1 gives me 3. So the slope of the secant line between those 2 points is 3. Now that's cool, but it's not terribly exciting because it is stuff that we already know how to do. There's a little bit of review. What I'm going to do now in this next problem, I'm going to start it off the same way. Find the slope of the secant line. So I'm actually going to be using that same formula. And you can look between x equals 1. So okay, x equals 1 is staying the same. But I'm going to change that second point. First time I had x equals 2. Now I'm going to change it to x equals 1 plus h. And you might be saying, whoa, hold on there. Why am I have this other variable? What's going on here? In order to perform this approximation, I need these 2 points, 1 and then whatever my second point is, I need those to be very, very, very close to each other. Now you might be thinking, well, x equals 1 and x equals 2, those are already pretty close to each other, but in the grand scheme of things, in the big wide world of math, they might as well be a million miles apart. I want some control over what that second point is. So if you kind of plot this on a number line and say, okay, here's 1, and then there's going to be some other mystery point right here. And to get to that mystery point, I'm just going to add some number here. I'm going to add plus h. So this point right here would be 1 plus h. And I can, check this here. If h is 1, if I chose h equals 1, then I would have 1 plus 1. This point would be 2, which is exactly what I had last time. So what this allows me to do is control what this number is, and it controls how far away this second point is, depending on what number I choose for h. I might want h to be 0.5. I might want h to be, if I want to get close, I might want h to be 0.1 or 0.01 or 0.001, and I can just keep getting closer and closer and closer until we get the idea. So that's why I'm using 1 plus h. That's why I am introducing this other variable. But don't get too worried here. We have this other variable, but we're still using the average rate of change formula. We're still going to fall back to that right now. So I'm going to plug in 1 and 1 plus h into my average rate of change formula. So f of 1 plus h minus f of 1 divided by 1 plus h minus 1. Now here, this one's a little bit more complicated than it was last time because I want to take 1 plus h and plug this into my function f of x. So I'm going to do a little bit of scratch work off to the side in the margins here. I'm just going to see if I can figure out just what is f of 1 plus h first, and then I'll go ahead and plug that in. So f of 1 plus h. Remember, I'm plugging that into f of x equals x squared. So this will be 1 plus h quantity squared. And to square something means to multiply it by itself. So this really says 1 plus h times 1 plus h. I'll have to FOIL that out. And when I do, I'll have 1 plus h plus h plus h squared. Combining my like terms gives me 1 plus 2h plus h squared. And just so that we have everything kind of in the same spot, I'm also going to find f of 1. We did that in the last problem, but just so that we have it all in one spot, f of 1 is 1 squared, which is just 1. So I've done this work off to the side over here, but now I can take out this f of 1 plus h and replace it with 1 plus 2h plus h squared, because I've already done that work. So let's hop back to our problem here. We'll have 1 plus 2h plus h squared minus f of 1. Well, we said that was 1 right here. We found that over on the right-hand side. Divided by, in my denominator, I can start to simplify a few things. I can look at this and I can say, well, I've got 1 minus 1 right there. Well, those two are going to cancel, and I'll just have a single h in the denominator. Oops, let me make that blue. I'll just have h in the denominator. In the numerator as well, I can simplify that. Again, I see 1 minus 1. Those two are going to cancel. So all I'm left with in the end is 2h plus h squared divided by h. And I look at that and I think that looks like it can be simplified. We can go a little bit further with that, particularly in the numerator. Both of those have a common factor of h, so let's factor that out. That will leave me with 2 plus h divided by h. And then what that allows me to do is cancel that h from the numerator and the denominator. So the slope of the secant line between 1 and 1 plus h is m equals 2 plus h. And what this allows me to do again is to choose how close this second point is. If I want to use 0.001, I would use h equals 0.001, and then I could plug that into this equation to find the slope of the secant line. It's actually quite helpful for us in this problem. So I've got the slope of the secant line between x equals 1 and x equals 1 plus h. I said earlier that we studied limits, and there's a reason why we study limits before we start to answer this big question, and that's because we need limits here. So in part C, I'm going to apply the limit as h approaches 0 to our answer from part B. So I'm going to find the limit as h approaches 0 of our answer from part B, which was 2 plus h. This is a relatively straightforward limit. We can just plug in 0. 2 plus 0 gives me 2. So that is my limit. Part D, here's where the exciting revelation happens. Interpret your answer from part C. So just to draw out what we've done, we were working with a parabola. We were working with, say, y equals x squared. And let me draw in a parabola right here. And we said we wanted to work with x equals 1 right here. Actually, let me do this. X equals 1, and then this other point right here, we started off with 2, but then we said, no, 2 is too far away, so we're going to use 1 plus h instead. So we use these 2 points, 1 and 1 plus h. Again, remember, I'm just adding a little h to get to that second point. And now look at what happened. And let me just actually take a step back before I jump into part C. Remember, in part B, we've done a lot here so far, but in part B, this was the slope of the secant line between those two. So we found the slope of the secant line. We sort of just connected the dots between those 2 points. Pardon my not straight line. In part C, look at what we did with h. We applied the limit as h approaches 0. So what happens as h gets very, very small? So I'm going to imagine, well, what happens to this point right here as h gets very small? Well, this point right here, it's going to get a little bit closer to 1, and then a little bit closer to 1. It's just going to keep moving closer and closer to 1 every single time as we get closer and closer to 0, which is kind of what a limit is. So we said, okay, maybe here's 1, and then we move h a little bit closer. And we say here is the slope of the secant line that time. And maybe we'll draw in one more example. We'll say here's 1, and then like 1 plus h would be right here. What we're getting close to, hopefully you're starting to recognize it, is we're getting really, really close to the slope of the tangent line at x equals 1. And that's what this answer from part C represents. It says if you take that other point, if you take 1 plus h and move it as close to 1 as possible, you will find the slope of the tangent line. So if I wanted to talk about, well, what does this problem mean? Why have I spent so long on this one problem? Part C, m equals 2 is the slope of the tangent line to our function f of x equals x squared at this particular x value that we were working with is 1. So if I were to graph x squared, and let me do that one last time here, if I were to graph my parabola of x squared and say here is x equals 1 and sketch in the tangent line, which we know looks like this, I know that the slope of that tangent line is 2. And that's a really, really big deal because that helps us answer that question. That helps us answer, how do we find the slope of the tangent line? Well, just to kind of review what we did here, we started with the slope of the secant line between these 2 points. And then we took that second point and moved it as close as possible to that other to our original point, to x equals 1, and that's how we found the slope of the tangent line. So we used what we knew about slope of the secant line and limits to help us find slope of the tangent line, which is very, very cool. I'm going to post a link after this video that you can hopefully kind of play around and move points around and actually see how the slope of the secant line approximates the slope of the tangent line as we get closer and closer. So take a couple minutes to kind of experiment and play around with that for yourself.